So we defined interpretations of formulas inside models, inside structures, and then we explained that if you have a sequence like this with formulas phi and psi, you say that M models the sequence provided this sub-object is strictly less than this sub-object when you consider the ordering inside the sub-objects of the corresponding ambient object. So therefore, we can talk about M satisfying a theory if M satisfies every sequent in that theory, and we obtain the category of T models inside category C, and of course that's the full subcategory of sigma structures inside C whose objects are models of the theory T. And to show how unusual things can happen, I prepared a little example in my kind of favorite case of the topos of different sets or n actions of the additive monoid of natural numbers. So let's take some two sorts, A and B, and the formula phi will be existential, and the formula psi will be universal. And the topos that we're going to interpret these formulas in is, as I said, Bn, the classifying topos of the monoid n plus. And you take M, a structure in S, and let's see what these interpretations look like. So for the existential formula, you get the set of all B. So, okay, when I have a action of n plus by this kind of by this symbol, I mean the underlying set. Okay, so MB is going to be an action of n, and by this symbol I mean just the underlying set of that, forgetting the action. All right. So because it's an underlying set, I can speak of its elements. So, okay, so this object here, on the other hand, this object has to have an action of n. All right, so I'm defining an action of n. It's going to be the set of all B in the underlying set of MB, because this is the type of Y, such that there exists A in the underlying set of MA, so that AB belongs to the interpretation of theta inside M. That is pretty much as expected. Okay? Now, the action on these things is going to be inherited from MB itself, right? So n dot B is simply going to be the inherited from MB, and you can sort of show that this condition make this set closed under the action. So it's really an action. Okay, so this looks as expected. This would be exactly the same if we were interpreting this inside sets. Now, let's take a look at what happens with the universal quantifier. So, with the universal quantifier, you get a set of those B in the underlying set such that for every natural number n, for every A in MA, A comma n dot B belongs to the interpretation of this. Now, without this condition, so if I just wrote A comma B, this would not be closed under the action of n. All right? So this is indeed necessary. And every universal quantification in this topos produces another universal quantification over the natural numbers. So I leave it to your imagination to, for example, imagine what would it look like to define the kind of supremum of a set using this, because to define the supremum as the kind of least upper bound, you need several exchanges of quantifiers, and for each of those you would get another quantification over the natural numbers, and the expression would be rather complicated indeed. Okay, so this is, it has to be like that, but you kind of get used to it, and after a while it becomes kind of reasonable. Okay, so we know what models of theories are. Let's see how we can classify them using classifying toposes. Now, before we get to the classifying toposes, I should tell you what this categorical logic, what nice properties it has. So this is the parallel to the soundness theorem from ordinary first-order logic. So if T is a Horn or regular or coherent or first-order or geometric theory, sigma the same type of sequent, and C the corresponding type of category, then if T proves sigma in the intuitionistic deductive system, so it has to be intuitionistic deductive system, then for every model of T, M satisfies the sequent. So this is as expected. Now we kind of work towards the construction of classifying toposes. We do this by going through so-called syntactic categories. So a syntactic category for a regular, coherent, first-order or geometric theory T is the corresponding type of category denoted CT, whose objects are equivalence classes of formulas and morphisms between these equivalence classes of formulas are provably functional formulas. So basically formulas whose somehow, okay, if you have this x dot phi and another formula y dot psi, then a morphism would be defined by a formula theta in x and y so that it defines the graph of a function. So it has to have unique values, right, and be a function in a provable way. So the theory proves that this is somehow a function. And so this is purely kind of syntactic construction. Everything is up to provability. And then inside it, you can define in a rather tautological way the generic model M sub T of T. Okay, because you simply take somehow you take the sequence of T and look at the corresponding equivalence classes, and these somehow give you, in a rather tautological way, a generic model. And what follows from this construction is a very easy completeness result. So if you have T, a regular coherent first order or geometric theory, sigma the same type of sequent, if the formula, if the sequence sigma is satisfied for all models of T, ranging over suitable categories, then T proves sigma. Suitable means the same choice as here. Okay? And the reason why it's so easy, I say, is that the sketch of proof is like one line. You can show that T proves sigma if and only if the generic model proves sigma. Now this you can't really do in first order case because you're unable to change the category. So, okay. Now another good property of the generic model is that any other model can be obtained as an image of the generic model. So this is the statement of this theorem. So for any regular coherent geometric category D, you have an equivalence of categories where you consider regular coherent or geometric functors between the syntactic category and this D, and T models inside D. And the equivalence is realized by the functor taking, so if you take, say, a geometric functor between CT and D, call it F, you simply evaluate it on the generic model, and somehow the statement is that every model is hit by one of these. So somehow all models are images of the generic model. Okay, so now we come to the definition of a classifying topos. So, okay, start with a geometric theory, T. Of course, you can have variants of this theorem for other kind of smaller fragments of logic as well. But let's do it for the most sophisticated case. So for any geometric theory T, there exists a classifying topos denoted set angle brackets T, which also has, so in this topos, you have a universal model called UT now. So this is kind of different from having the generic model, because generic model is in the syntactic category and universal model is model of the theory in the classifying topos, such that for any Grothendieck topos E, the topos morphisms from E into the classifying topos, the category of those is equivalent to the category of T models inside E. So these functors here, so you can, if you imagine this as a sort of a space, functors into the space from E can be sort of considered as E-valued points of that space. So E-valued points of the classifying topos are models inside E. That's why it's called classifying topos. It's a space whose points are models. And what is the functor realizing this equivalence? So if you take a geometric morphism from E to the classifying topos, you obtain T model in E by taking the inverse image of the universal model. So that's correct because you see the universal, the inverse image goes from this category to here, and UT is a model here. When you pull it back, you get a model, you get a structure in here, but because the inverse image functors preserve models, you get a model in E. So this is somehow what the classifying topos is. It's not such a very easy thing to kind of imagine, and I remember a Durham symposium, which is a sort of almost 2 weeks long conference where we had model theory community and category theory community. It was a long time ago, and yeah, this was, for me as a model theorist, a very difficult thing to grasp back then. And I don't think any of the category theory people attempted to give this technical definition. So, yeah. But somehow you should think of it, you know, this classifying topos is a sort of a space whose points correspond to models. And this becomes even clearer when you choose for E the topos of sets. So, okay, first of all, the T-modeled topos. So when you say a T-modeled topos, what you mean is actually a pair consisting of a topos and a model of T inside the topos. So that's a kind of T-model topos. So if you say, for example, a ringed topos, which is very common in algebraic geometry, for example, you mean a topos together with a ring model of the theory of rings inside that topos. Or alternatively said, you're thinking of a topos and a ring object inside that topos. Right, so the above universal property determines the classifying topos uniquely up to equivalence. And now what I wanted to say is when you specialize the above property to the case of sets, then, then this becomes the category of morphisms, of geometric morphisms from set into this topos, and that is what we call the kind of points of a topos. So points are geometric morphisms from the category of sets. So this is exactly the category of points of this somehow space. And then on the other hand, the right-hand side becomes the category of set models of T. So what I was previously, what I previously mentioned, kind of with E-valued points, becomes a lot more concrete now, because this means that the category of points of set T is precisely the category of set theoretic models of the theory. So really, the points of this kind of space are models of T. Okay. Now, a similar thing works more generally. So you note the kind of rather weird notation, set angle brackets T. So this indicates that you're working over the base topos of sets. And in fact, that means that you're working with Grothendieck toposes, which have a canonical morphism into set. But you can work over an arbitrary base topos S. And if you take a theory over S, it's not so easy to explain what that might be, but that would be a theory that kind of mentions certain fixed objects from S as a kind of parameters. So S would be like a parameter space for that theory. Then you have this situation, the classifying topos S of t is a topos over S, so it has a geometric morphism into S, and you have this, the above equivalence becomes topos morphisms over S, so these are kind of triangles, right? So E must be over S, and this guy is over S, and you're looking at kind of triangles like that. Okay, so these relative topos morphisms from E to S of t correspond to t models in E. All right, let me give a sketch of proof of the theorem of existence of classifying toposes. As I mentioned, it uses this syntactic category, but moreover, we must also define the syntactic topology Jt on the syntactic category. And okay, as I said, this is what morphisms look like. So formulas describing morphisms in the syntactic category are provability classes, T probability classes of formulas like that, okay, which have two blocks of variables, and they correspond to kind of domain phi and codomain psi. And for the coverage, to define the coverage, we need to declare which of these constitute a covering. And this is what we do. We declare that such a family is a Jt covering whenever you have this sequent and it's T provable. So somehow, if you think about what this says, it's almost like saying that the union of images of these maps cover the bottom, okay? Cover the target. See, this says that the target is, think of kind of interpretations. So this means that the interpretation of the target is less than or equal to the union of these guys, and these are precisely the images of these imaginary functions. Okay? So this is the syntactic topology, and the classifying topos, we claim that it is the category of sheaves on this site, so syntactic category equipped with the syntactic coverage. And the universal model is going to be obtained in a rather easy way from the other one was, what are they? Universal, and the other one was generic. Yeah. So the universal model is the image of the generic model under the kind of Yoneda embedding. So canonical embedding of CT into sheaves on this site. So, okay, now we need to prove, so we claim that this is the classifying topos and that this is the universal model, but we still need to prove the universal property. And, all right, so we must figure something out about the category of topos morphisms from E into this sheaf category. And luckily, there's a theorem of Diaconescu which explains precisely this situation. So Diaconescu's theorem tells you that this is equivalent to the category of torsus, or in other words, flat JT continuous functors from CT into E, whatever that means, so we can't go into details. And then you can sort of check that this is the same as geometric morphisms from the geometric syntactic category into E. And that, by one of the previous theorems, is precisely T mod of E. And that's the end of proof. So, in a similar way, we have sort of an extension of this completeness theorem. So where is it? The completeness theorem was somehow dependent on sigma being provable if and only if the generic model satisfies it. And here we have the same thing with the universal model. So geometric sequent is T provable if and only if the universal model satisfies it. Now, so this, I'm kind of copying what I saw in Laforgue's talk in Topas's online conference, how somehow there's this remarkable connection between Gödel's completeness theorem and the Lean's theorem about coherent topases having enough points. So this is proved in a kind of very topos theoretic way, and the reason for proving this was in order to prove results in algebraic geometry. And okay, what is the connection? What is the connection? Well, sigma is T provable if and only if the universal model satisfies it. So if you have a point, so we said a point is a geometric morphism from set to the classifying topos. So if that's a point, then pulling back a model along the inverse image map of the geometric morphism is another, well, also satisfied. It preserves provability. So, on the other hand, this really is a T model of inside sets. So, altogether, if you have points in your classifying topos, then you have completeness theorem. Okay. Now, right. Okay. So let me now show you a couple of examples of what these classifying toposes look like, and I want to kind of I announced that we would be going in the direction of developing algebraic geometry in a topos. So I'm going kind of with examples leading towards algebraic geometry. So if T is an algebraic theory, then the classifying topos can be presented in a relatively straightforward way as simply a pre-sheaf topos on the category of finitely presented T models in set. So there's no need to impose the topology, the syntactic topology. And the universal model simply corresponds to somehow the embedding of finitely presented models into all models and then forgetful functor into set. Okay. So It's a very simple situation, and therefore, for something relevant for mathematics, like, say, the theory of commutative unital rings, you see that the classifying topos is simply the category of presheaves on the category of finitely presented rings. Okay. Now, just bare rings are not quite what's going on in algebraic geometry. So let me list another fact which describes a situation where you have a sort of, you start with T0, an algebraic theory, and then you add a couple of coherent axioms. Okay, so you start with an algebraic theory, you add a couple of axioms coherent of this type to obtain the new theory called T. And then the claim is that the classifying topos, this should be, I think, angle brackets, is the category of sheaves as before, as in general, but the syntactic topology can be described relatively explicitly using the shape of these axioms. So the syntactic category, syntactic topology is generated by families which are very directly, I mean, you don't need to bother reading these formulas, they're rather complicated, but the point is that you have a description of the syntactic category rather directly in terms of these axioms that you added, these coherent axioms that you added. And moreover, you can then even go a step further. You can replace this rather abstract category of syntactic category by the category of finitely presented T0 models in the category of sets. Example, local rings. So the theory of local rings is a quotient of the algebraic theory of rings, and you introduce another coherent axiom which says that every element of your local ring, either the element is invertible or 1 minus the element is invertible. Okay? This is not how we usually define local rings. We usually say it's a commutative unital ring which has a unique maximal ideal. But that's not really a nice intuitionistic axiom to say, right? So you find another classically equivalent definition, but which makes more sense intuitionistically, which is this. And now, what do we get for the classifier of local rings? So this is the category, using the previous fact, is the category of sheaves on the site which consists of finitely presented rings, and then the opposite category, which you can sort of think of as finitely presented affine schemes. So there's some kind of geometry coming in with the Zariski coverage, and Zariski covers are of the form. So, okay, because we're working in the opposite category, the arrow here is going somehow in a very confusing direction. What we really should be thinking of is this is the localization morphism from A into A with Si inverted with an element inverted. So this is the kind of algebraic morphism goes in this direction. It's just a localization morphism. But because I'm working in the opposite category, I need to write the arrow going that way. So such a collection is a cover, is a Zariski cover, whenever the ideal generated by S1 up to Sn is the unit ideal. And thinking geometrically, that really means that if you think of kind of spectra of these rings as schemes, that would really mean that the union of the images of these scheme theoretic maps covers the domain. Okay. Now then, the universal model is simply corresponds to the forgetful functor from finitely presented rings into set. And you have to kind of think a little bit, how do you see this functor as a ring object in this category of sheaves? But somehow you need some facts about this Zariski topology. You need to know that it's subcanonical, whatever that means. But this can be done. And as I already said, this site should really be thought of as affine finitely presented schemes with Zariski coverage, which is very close to being the affine big Zariski site, which is naturally considered in algebraic geometry. So there are big sites and small sites, and this is the big version. All right, so given that purely from considering kind of classifying toposes, we get big sites relevant to algebraic geometry, how do we get schemes and small sites from algebraic geometry? Well, by using the so-called Hakim-Kohl spectra. So Hakim was one of the rare successful students of Grothendieck, and she wrote her thesis in maybe 50s, and it was published as one of the Springer monographs in the 60s. And then I think she changed subject and worked in a completely different area. But this is a really interesting book, and it was recommended to me by a colleague, Meher Nuhi, and at first I didn't see that this was relevant to what I was trying to do. But then after some time I realized that it was like the thing that I was looking for. And then Kohl, so Hakim proved this theorem that I'm about to describe for the special case of rings and local rings. So this kind of passage from rings to local rings. And Kohl generalized it to the present statement for arbitrary theories. I mean, for suitable quotients of more general theories. So what are the ingredients? So we have S and T, two finitely presented geometric theories in the same language, same signature, such that T is a quotient theory of S. That simply means that T is obtained by adding more axioms to S. Now, you also fix A, an admissible class of morphisms of T models. Now, why is this needed? Let me explain on the example of rings and local rings. So, think of S being the theory of rings and T being the theory of local rings. What are homomorphisms of local rings when you think of them as models of T. Homomorphisms of local rings thought of as models, unfortunately, are just ring homomorphisms. But they're not necessarily local homomorphisms of local rings. So they don't necessarily preserve the unique maximal ideal. So that's unfortunate. So what we really want is not just pass from the theory of rings to local rings, but we also want to consider local rings with local homomorphisms of local rings, okay? And that's why this A, this class of morphisms is there. Okay, so, I mean, it's supposed to be an admissible class and have a certain list of nice properties in order for you to be able to do this, but, okay, S top is going to be the two category of S-modeled Grothendieck toposes. So as I pointed out earlier, S-modeled Grothendieck toposes are just topos, a pair consisting of a topos and a model of S. And then A top is the sub-two category of T top, so of T models, whose one arrows arise from the admissible class in this way. So one arrows look like this. It's a pair consisting of a geometric morphisms of the underlying toposes and an arrow from the pullback of M to N. Note, you can't really talk about an arrow from M to N because they live in different toposes, so you have to sort of pull M into the same topos, and then this is now somehow an arrow in F, but belonging to this admissible class. Right. So Cole's theorem says that the inclusion two functor from A top into S top, so this is purely because any kind of model here is a model here, and any morphism here is also a morphism here. So you really have this inclusion. But it admits a right to adjoint called spectrum. And Hakim proved this version of this theorem for S, the theory of rings, T, the theory of local rings, and A, the class of local homomorphisms of local rings. And in that case, the right to adjoint to the two inclusion between locally ringed toposes and ringed toposes is called the Zariski spectrum. So the Zariski spectrum is a functor that takes a ringed topos. So it takes a ringed topos, SA, and produces a locally ringed topos called spec ZAR of SA. So it's going to be a topos, let's say S tilde, with a ring object which happens to be a local ring. So now what's quite essential is that you have to remember its sort of structure morphism into the original ring topos. You obtain this kind of structure morphism back into the original ringed topos, and I'm going to call it pi ZAR because this is somehow Zariski topology we're talking about, and I'm calling this structure map pi ZAR. And it satisfies a certain universal property, which can be obtained by simply unraveling the definition of being a two adjoint to the inclusion functor. Now, the same thing can be done, so Hakim shows how the same thing can be done for an arbitrary scheme Grothendieck topology tau. And these are topologies which are in regular use in algebraic geometry. So first of all, you have this as a risky one, and then a tau topology, various flat topologies. And so for any tau from this rather long list, you can define the tau spectrum, which I will denote spec tau of SA, together with this structure geometric morphism to the original ring topos. Now, Gavin Wraith showed that the spec tau is the right two adjoint of the inclusion of strictly locally ringed toposes into ring toposes. So basically, he showed that for the tau case, the tau spectrum corresponds to the passage from the theory of rings to the theory of strict local rings, or in other words, that the situation is closely tied to, some kind of classifying topos of strict local rings. But even though you can define these spectra for FPPF and FPQC topologies, so far we don't know precisely which geometric theories they correspond to. So it's not explicitly known. And people are kind of thinking about this still. Now, all right, so this basically, if you ask me what is kind of a relative affine scheme, I will tell you it's one of these guys. So relative means that you don't start with an ordinary ring or a ring in the category of sets, but you work in a topos S, and you take the ring object in S, and then you want to define its spectrum. So it's this, okay? So the point is that you should think of it as a ringed topos and not a ringed space. A lot of researchers attempted in various situations to define spectra, but they were trying to do it by describing these spectra as ringed topological spaces. And that cannot be successful. And however, this approach seems general enough for a lot of interesting developments. Now, Hakim goes further and doesn't consider just affine schemes, but defines more general S schemes, so schemes over a base topos S. And for any scheme topology tau, you obtain a T realization functor. So T realization of X is some topos X tau and some tau local ring, whatever that means, where you have this picture. So you have the structure morphism to S, Then you have the global sections functor. Okay, I'm assuming S is a Grothendieck topos. So you have the global sections functor to the category of sets. And then the composite from here is somehow the global sections of this Grothendieck topos. And this picture allows us to now start doing relative algebraic geometry. And for example, you can define relative cohomology. So let's try to retain this picture if possible. So if now you take an abelian group M here, or even O tau module over here. So this is a tau ringed topos, so it has this O tau ring. So you can speak of O tau modules in XT. You can define the tau cohomology, say ith tau cohomology of M with respect to the scheme topology tau as derived higher derived images of the this global sections functor gamma tau, and simply because this functor lands in set, what you obtain here is an ordinary abelian group model in set. However, relative tau cohomology, which I denote like that, is obtained by taking the higher direct images along pi tau, along this guy, and it lands in S. So these are in fact abelian groups inside S, and that's really in the spirit of working over a base topos. You're not interested in getting results, getting some invariance for your spaces that somehow live in the universe S. You don't want them to come out and go into set. You want them to be in the same universe. And for example, Hakim already worked out quite a lot of theory in the case of cohomology of quasi-coherent coherent sheaves for Zariski topology. And I'm developing results, following the classical theory. I'm developing relative étale and flat cohomology. And you see, in general, there are, in full generality, all you can obtain is fully general results, which basically tell you, okay, there's a certain spectral sequence which describes the situation. But in this, in my favorite case of difference sets, you can really calculate this explicitly and get some explicit nice results. Similarly, another important thing in algebraic geometry is that of, say, étale fundamental groups. And what you can do here using this picture is talk about the relative fundamental groupoid. And the reason for having to go into groupoids and not groups is that your topos may not have points. So you see, when you're talking about fundamental group, you must select a base point in your space. But if your topos doesn't have a point, then the best you can do is consider the fundamental groupoid. And this also happens in the difference case. And how do you do this? Well, you consider the structure morphism into S. and you use certain formalism of sort of topos theoretic Galois theory for p-determined toposes by Marta Bunge, and that will give you what kind of groupoid? Well, you know that in the classical case, Galois groups are profinite groups. So you have to consider topological groups. Now, in an arbitrary topos, topological spaces are not necessarily meaningful. So you have to use the best substitute you have, which is the theory of locales, which I mentioned in the last lecture. So you're going to get some kind of localic groupoids and possibly some kind of projective systems of those. And in the special case for difference sets, we kind of scratched the surface with my collaborator Widmer, and we kind of worked out the Galois theory of difference ring extensions, and it becomes really, really complicated. So the groupoids that you obtain actually turn out to be objects of symbolic dynamics. So they are totally disconnected spaces, things like Cantor sets with self-maps. So really, you go into a completely different realm of dynamics, and I think this is a big kind of step forward from previous attempts on difference Galois theory, because they often considered cases where your rings are assumed to be integral domains, therefore the spaces are connected and everything is very close to the case of fields. But we realized that you have to kind of remove these assumptions, and as soon as you remove them, you get extremely complicated behavior. Now, okay, so I'll conclude here by talking about the benefits of this type of approach, and what sort of results can you hope to obtain following this strategy of developing, say, relative algebraic geometry. First is a rather kind of basic observation that algebraic geometry over the classifying topos of some group or a monoid, I mean as long as they're discrete, corresponds to G equivariant algebraic geometry. And people do consider these from somehow first principles, but they simply define everything. What does it mean to be G equivariant, etc., etc.? But all these definitions fall out as properties when you develop algebraic geometry following this strategy over the base topos BG. So you don't have to kind of guess your way in this direction. You have a template, you have a very vast and developed theory which gives you a template for relative algebraic geometry. So you don't need to kind of guess for each particular G what it might mean to have a G equivariant algebraic geometry. And so, I've already shown that even for the simplest possible case of the additive monoid of natural numbers, you get significantly improved results in difference algebraic geometry to anything that existed before. So why are we optimistic for the success of this program? Because of somehow the old principle of topos theory, which says that any topos can serve as a universe for developing mathematics. So it should be possible to do this. Yeah. Okay, that's where I'll conclude. Thank you very much for listening.